So this is the final exam review, and if you're in my class, the final exam is always an optional test, so you absolutely never have to take the final exam. If you've missed the test, you likely will benefit from taking the final exam. If you have a really low test, you might benefit from taking the final exam. But you should know that before you go down the path of studying for the final exam, exactly what you need to get on the final to improve your grade. So you don't want it to be a mystery. So in the final exam review, it doesn't review everything from the semester. If something isn't on the final exam review, it won't be on the test. But the final exam review might not be enough for you to prepare for the final exam. For instance, when I solve a problem that has a fraction and an equal sign, like problem 1, well, for me, I know how to do this, so seeing one jogs my memory, reminds me of the tricks that I need to remember. But you may have to go back to section 2.5, where I think this came from, and do some more problems. So if you feel like one of a style of problem isn't enough and you're not sure where to find more, let me know and I can tell you exactly what section to look for more problems. So in this problem 1, it's from chapter 2. It has a fraction with an equal sign, and the first step usually in any problem that has some factoring is to factor. So this denominator of x squared minus x minus 12, it better factor into the other two denominators, and it does. It's going to factor. My signs are going to be plus and minus. My firsts are going to be a couple of x's. My last need to multiply to negative 12, subtract to be the number in front of the x there, which is negative 1. So I'm going to multiply by x plus 3 times x minus 4. And now I'm going to multiply by a fraction over 1 to clear the fractions. And it's just going to be the two components of the denominator. So I'm going to multiply by x minus 4 times x plus 3 over 1. And then x minus 4 times x plus 3 over 1. And x, well, it doesn't matter the order I put it in, minus 4 times x plus 3 over 1. Now I'm going to cancel the fractions. First, the x minus 4's cancel. They technically turn into 1s. All I have left is 1 in the denominator from this first fraction, so I don't need to write a fraction anymore. What's left is 3 times x plus 3. Second fraction, the x plus 3's cancel. They technically turn into 1s. Leaves me with only 1s in the denominator, so I don't need to write a fraction anymore. What's left is 5 times x minus 4. And to the right of the equal sign, both the x plus 3's and the x minus 4's cancel. Again, they all turn into 1s. I don't need to write a fraction anymore because all I have is 1s in the denominator. And the only thing that's left in the numerator is a 7x. Now I'm going to clear the parentheses and get 3x plus 9 plus 5x minus 20 equals 7x. I'm going to combine like terms on the left side. I'm going to go 3x plus 5x and 9 minus 20. When I do that, I get 8x minus 11 equals 7x. And I'm going to minus 8x and then divide by negative 1. So minus 8x minus 8x. This gives me minus 11 equals to minus 1x. I'm going to divide both sides by minus 1. And I'm going to get an answer that I'm absolutely going to check, because anytime I solve a problem that has an equal sign, it's not that hard for me to check, although it's moderately a nuisance here. So to check, I need to do each side separately. I'm going to throw my checking right up next to the original problem. So for checking, I need to put 11 in for the x's. The left side's going to be 3 over 11 minus 4 plus 5 over 11 plus 3. And I have to make sure that that equals 7 times 11 over 11 squared minus 11 minus 12. I'm going to do each side separately, and hopefully they equal to the same number. So left side, fraction 5 over 11 minus 4, get out of the denominator, plus fraction I messed up on that first fraction. It's supposed to have a 3 up top. So I'm backing up, changing that 5 to a 3. Now getting over to the second fraction. Second fraction, 5 over 11 plus 3. So I think I've successfully entered the left side. When I reduce it, it comes out to 11 over 14. Now I'm going to reduce the right side. So fraction 7 times 11 over, and I could put the 11 in parentheses, but because it's not negative, it's not really necessary, and I'm just saving a little time. So that's the right side. Also reduces to 11 over 14. So I'm 100% sure that my answer is correct. So every problem on the review that has an equal sign in the problem, I'm certainly going to take the time to check, so I'm making sure I'm not making a mistake. Problem 2, we can kind of check, but it's not as nice, the checking, because it doesn't have an equal sign. This is a factoring and canceling problem. I'm going to do some side work because the factoring is bottoms up factoring. So I need to factor 2x squared plus x minus 3. I'm going to do bottoms up. First I'm going to multiply, and I'm going to get x squared plus x minus 6. So the steps for bottoms up are multiply and then factor. So I'm going to factor that into x plus 3 times x minus 2, and then divide, reduce, and bottoms up, all kind of in one step. I started off multiplying by 2. I'm going to divide by 2. First fraction doesn't reduce, so I bottoms up and get 2x plus 3. Second fraction does reduce, and I get x minus 1. So I can take the original problem and rewrite the denominator to be 2x plus 3 times x minus 1. Now I can cancel the 2x plus 3's. When I go to write my answer, I can't just say it's x minus 1, because the x minus 1's in the denominator. It needs to stay in the denominator. I've canceled the entire numerator, so I need to leave a 1 behind. The checking that we did is we took a number like 2 and plugged it into the original problem and plugged it into my answer. If they come out to the same result, I think I'm okay. So I'm going to let x equal to 2 for my check, and I'm going to go to the original problem and go 2 times 2 plus 3 over 2 times 2 squared plus 2 minus 3, and then I'm going to do my answer, 1 over 2 minus 1. Both of those fractions have to equal the same number. If they don't, I've messed up. So original problem, plugging 2 in for x, fraction 2 times 2 plus 3 over 2 times 2 squared plus 2 minus 3. I get 1. Original problem, when I do the same strategy, go 1 over 2 minus 1. I also get 1. Because plugging 2 into the original problem and into my answer, I get the same simplification. I think my answer is right. That's not a 100% guarantee, but it's the best check I could do. 3a is a friendly problem. Adding when you have equal denominators is much easier than adding when you don't have equal denominators. When you add problems with equal denominators, you can immediately make the two fractions into one by writing the numerators next to each other. I'm going to simplify the numerator. I have a 2x plus x and a plus 10 minus 4. A 2x plus x is going to reduce to be 3x. A plus 10 minus 4 reduces to be positive 6. When you add or subtract, you should always try to simplify the numerator by factoring. The numerator factors. When I factor the numerator, I factor out a 3. There's an x plus 2 left over. The x plus 2 that's left over cancels with the x plus 2 in the denominator, cancels out the entire denominator, so my answer doesn't need to be a fraction. My answer is just going to be the number 3. There's no x in my answer, which means no matter what number I plug for x into the original problem, if it's part of the domain, it should also equal to 3. So I'm going to sneak my checking over here. I like letting x be 2. 0 and 1 aren't the best numbers for checking because sometimes, 0 times 0 is 0, 1 times 1 is 1. Sometimes it hides a wrong answer. But 2, if it's in the domain, generally doesn't. So I'm going to go to the original problem and go 2 times 2 plus 10 over 2 plus 2 plus 2 minus 4 over 2 plus 2. And in order for my answer to be right, this has to reduce to 3 because the answer not having an x in it says no matter what number I plug in for x into the original problem, my answer has to reduce to 3. So let me try this. So fraction 2 times 2 plus 10 over 2 plus 2 plus fraction 2 minus 4 over 2 plus 2 equals 3, which is exactly what I need it to be. So 3a I know is correct. 3b, much, much worse problem by a ton. I need to factor the denominators first. First denominator is easy factoring. It's a difference of squares. It's going to factor into z plus 3 times z minus 3. Second fraction is going to factor, its denominator is going to factor into z plus 3 times z plus 1. The very first problem I did on this review had an equal sign, and I multiplied by a fraction over 1. To clear the fractions, this problem doesn't have an equal sign, so I can't multiply by a fraction over 1. I have to multiply by something over itself, and I can't clear the fractions when a problem doesn't have an equal sign. So what I need to do is multiply each fraction by something over itself to make each denominator have the same components. So multiplying the first fraction by z plus 1 over z plus 1, the second fraction by z minus 3 over z minus 3 makes both denominators have the piece z plus 3, z minus 3, and z plus 1. When we're adding fractions, we generally never multiply out the denominators, but we generally always multiply out the numerators. So the left numerator, I'm going to go 4z times z is 4z squared. That's 4z times z. And 4z times 1 is going to be plus 4z. The right numerator's FOIL. Z times z is z squared. Z times minus 3 is minus 3z. The inner part of the numerator is 2 times z, which is plus 2z. The last is 2 times minus 3, which is minus 6. The outers and the inners combine to be a minus z or a minus 1z. So I get z squared minus 1z minus 6. Each denominator has the same 3 pieces. It doesn't matter which order you write the pieces in. You can shuffle the parentheses around and it still is going to be equal to the line above it. And I usually just pick an order and make both fractions have that same order. But you can definitely write your denominator in a different order. Now I'm prepared to make the 2 fractions into 1 because they have the same denominator. So I'm going to go 4z squared plus 4z plus z squared. That z squared is really a 1z squared minus 1z minus 6 over the 3 pieces z plus 3 times z minus 3 times z plus 1. Now in the numerator, I'm going to add 4z squared plus 1z squared and get a 5z squared. I'm going to take 4z minus 1z and get a 3z, and I'm going to leave the minus 6. So I'm going to get 5z squared plus 3z minus 6 over z plus 3 times z minus 3 times z plus 1. Anytime I'm adding or subtracting, I should try to factor my numerator. So I'm going to attempt to factor this using bottoms up. Kind of side work, but I'm out of room for side work. So I'm going to bottoms up this. I'm going to multiply the 5 and the 6 and change this to z squared plus 3z minus 30. And for that to factor, I know my signs have to be plus and minus. And my lasts can only be 1 and 30, 3 and 10, or 5 and 6. 1 and 30 aren't going to help me get the 3 in the middle. 10 and 3 are going to give me a 7 in the middle. 6 and 5 is going to give me a 1 in the middle. This is prime. Since the numerator is prime, the numerator can't factor, and I would say this is my answer to this problem. Really unpleasant to check, but I'm going to check by plugging 2 into my original problem and 2 into my answer. So for checking, I'm going to check some up high and some up low. I'm going to go 4 times 2 over 2 squared minus 9 plus 2 plus 2 over 2 squared plus 4 times 2 plus 3. Figure out what that equals to, and then do the same with my answer. So for the original problem, changing the x's to 2, 4 times 2 over 2 squared minus 9 plus fraction 2 plus 2 over 2 squared plus 4 times 2 plus 3. The original problem, when I change the z's to 2, I get negative 4/3. Now I'm going to go to my answer and do the same. I'm going to go 5 times 2 squared plus 3 times 2 minus 6 over 2 plus 3 times 2 minus 3 times 2 plus 1. If it equals to anything other than negative 4/3, I'll go hunting for an error. So let me just do this where you can more or less see it. So fraction 5 times 2 squared plus 3 times 2 minus 6 over parentheses 2 plus 3 parentheses 2 minus 3 parentheses 2 plus 1 equals also negative 4/3. So I feel really good about my answer. I've checked it the best I can. So when we're adding fractions, multiplying fractions, dividing fractions, the checking isn't as nice as when we solve a problem with an equal sign, but we can still be fairly certain that we have a right answer by just taking the number 2, as long as it doesn't give me a domain error, and plugging it into the original problem in the answer. And if the numbers match up, you feel good about your work. For 4, to find the domain of a fraction, you ignore the numerator. So I'm going to ignore the y minus 4. I'm going to solve the denominator equal to 0. And then I'm going to write my answer. You can write your answer in interval notation, or you can write it in words. It doesn't give any restrictions here. So when I solve the y plus 1 equal to 0, I minus 1 from both sides and get y equal to minus 1. In words, you can say the domain is all real numbers except negative 1. In interval notation, to get an interval notation for a fraction domain, you create a number line with negative infinity and positive infinity on the edges. You put the number or numbers you're going to exclude from the domain on the number line, and you create intervals. So the domain for this in interval notation would be the interval from negative infinity to negative 1. Round brackets excludes a number, and then negative 1 to infinity. When we did interval notation, you put a U or a union symbol between the intervals. I'm completely content with either answer. If there's one you have a strong preference for, do it. It doesn't matter to me. Some college algebra teachers are really hung up on the interval notation, but I don't think it's significantly better than the writing in words, other than it's easier to write probably for a mathematician. So there's no number 5, but there's a number 6, which is a multiplication problem. We're still doing Chapter 2 problems. We haven't left Chapter 2 yet. Every problem I've done so far has been from Chapter 2. This is a factoring and canceling problem. The 5y plus 10 has a common factor of 5. When I factor 5y plus 10, I factor out a 5. I'm left with a y plus 2. The denominator y squared minus 4 factors into y plus 2 times y minus 2. When I check, I won't be able to plug 2 in for y because that will make my denominator 0, and that will give me an error. So this time when I check, I'm going to use 3. I don't like to check with 0 or 1. 2 will make a denominator 0, so I'm not going to check with it. When I check, I'm going to put 3. This numerator factors into y plus 4 times y minus 2. Barely readable. It's y plus 4, y minus 2. That denominator is a common factor of a 10. When I factor out a 10, I'm left with a y plus 2. So when I go to cancel, this single 5 will cancel with that single 10. The 5 becomes a 1, the 10 becomes a 2. The y plus 2 here will cancel with that y plus 2. This y minus 2 will cancel with that y minus 2. I've canceled everything that I can. And in terms of an answer, the only thing that's left in the numerator is a y plus 4. And in the denominator is a 2 times y plus 2. This is an okay, this is the best answer. If you multiplied out the denominator, it's okay. It's equivalently right, and neither version is reducible. You can't cancel the 4s in this version. You can't cancel the 4 with the 2 in this version. The nice thing is if you check, you'll catch that mistake. So I'm going to check by plugging 3 into my answer, which is easy. So the checking here, it's easy to go 3 plus 4 over 2 times 3 plus 2. When I plug 3 into my answer, fraction, whoa, fraction, got a little blurry on me there. Sorry about that. So hopefully my work wasn't totally muddy. I factored the numerator. I got 5 times y plus 2. The denominator, y plus 2, y minus 2. The numerator on the right, y plus 4, y minus 2. The denominator, 10 times y plus 2. I canceled this y plus 2 with that y plus 2. This y minus 2 with that y minus 2. This 5 with that 10. 5 divided by 5 was 1. 10 divided by 5 is 2. The only thing in the numerator I didn't cancel was that y plus 4. And the denominator was 2 times y plus 2. And you don't have to multiply out the denominator, but you could. I can't check with 2 because if I plug 2 into that fraction, I'd get a 0 in the denominator, and that would give me an error. So I'm checking with 3. And, so checking with 3. 3 into my answer, I'd go 3 plus 4 over 2 times 3 plus 2. And that gives me 7/10. And then I need to do the same to my original problem, which is much harder to do. But I'm going to go 5 times 3 plus 10 over 3 squared minus 4 times 3 squared plus 2 times 3 minus 8 over 10 times 3 plus 20. Notice I didn't throw any parentheses in. The 3 wasn't negative, so it made the parentheses not that necessary. And it's a lot quicker for me to enter times signs than it is parentheses. So I better get 7 over 10 when I do this. If I don't, I've made a mistake somewhere. So fraction 5 times 3 plus 10 over 3 squared minus 4 times fraction 3 squared plus 2 times 3 minus 8 over 10 times 3 plus 20. That's just putting those in. When I hit equals, I get 7 over 10, so I know I'm right. So in Chapter 2, the nice thing about Chapter 2 is basically every problem was checkable, which makes it maybe better than some of the later chapters where we might get some problems that aren't checkable. 7a, it gives me a function called g of x. It's a parabola, and to find the domain of a parabola, there's no algebra. If you did any algebra, you'd likely find the x-intercepts, and the x-intercepts have nothing to do with the domain. So the domain in words would just be all real numbers. And in an interval notation, it would be from negative to positive infinity. If you put any numbers in your domain other than the infinities, you're going to be wrong. If you factored this and set it equal to 0, pictorially what you're going to find are the x-intercepts of the parabola, which have nothing to do with the domain, because the parabola extends all the way to the left to the point negative infinity, positive infinity, all the way to the right to the double positive infinity. And the domain from a graph, you take the x-coordinate of the far left point, the x-coordinate of the far right point. Not supposed to really do that. If I see a polynomial, it means no fractions, no square roots, no logarithms. Its domain's just going to be all real numbers. The next thing I'm asked to find is g of 2. So I'm going to go 2 squared plus 5 times 2 plus 6. And I can do that with or without my calculator. This is going to be 4 plus 10 plus 6. That comes out to 20. For my answer, it would probably be nice to say g of 2 equal to 20. But if you just said 20, it would be fine. Better double check myself and do 2 squared plus 5 times 2 plus 6. And you get 20 just fine. Eights and 9 are super kind on this calculator. I'll do them by hand. To rationalize the denominator means to write an equivalent fraction that doesn't have a square root in the denominator. For question 8, since it's just a monomial in the denominator, I multiply by a copy of the denominator over itself. That's going to give me, in the numerator, 2 square root of 6. In the denominator, when we multiply by 2 identical square roots, we simplify by just writing what's under one of the square roots without the square root. Now I'm going to reduce the 2 with the 6. The 2 is going to become 1. The 6 is going to be 3. And my answer to number 8 is going to be the square root of 6 over 3. Nicely, I can check on my calculator. So for number 8, I'm just going to enter 2 over the square root of 6. And when I do that, it tells me exactly how it reduces. Question 9, I have to multiply by the conjugate of the denominator because the denominator has that plus sign in it. So I'm going to multiply the numerator and the denominator by 5 minus the square root of 7. In the numerator, I multiply negative 5 times 5 and get negative 25. And then negative 5 times minus square root of 7. When you multiply negative 5 times minus square root of 7, you're multiplying two negatives, so you're going to get a positive. And I'm just going to leave the 5 and the 7 next to each other. In the denominator, I have to FOIL. The firsts are going to be 5 times 5, which is 25. The outers are positive 5 times minus square root of 7, which is minus 5 square root of 7. The inners are the square root of 7 times 5, which is positive 5 square root of 7. The lasts are positive square root of 7 times minus square root of 7. That's minus square root of 49. So the 5 square roots of 7s will cancel. The firsts that are 25 and the last comes out to be 7 will reduce to 18. And I think this is the answer my calculator is going to give me. It might break this into two fractions, but I don't think it will. So I'm going to check just by entering this fraction. So fraction negative 5 over 5 plus square root of 7 equals, beautiful, negative 25 plus 5 square root of 7 over 18, negative 25 plus 5 square root of 7 over 18. So I've checked the best I could. 10 wants me to reduce the square root. I know in 10, because there's a negative under the square root, I'm going to get an I. And I'm going to do a prime factor tree to figure out how to reduce the 50. I'm going to go 50 equals shift factor it. So the prime factoring for 50 is 2 times 5 times 5. And in square roots, anytime you get a pair, you get one outside the radical. So this whole answer, I'm going to have a 5 to the left of the radical for them a pair of 5s, a 2 under the square root from the single 2, and an I after the square root outside the square root. If I want to check this on my calculator, I need to put my calculator into complex mode. So I go mode 2, and now I go square root negative 50, and I get 5 square root of 2i. Perfect. Next one, I need to reduce the square root of negative 18. So I know that's going to be 2 times the square root of 18 times I minus the square root of negative 50. I just figured out to be 5 times the square root of 2 times I, so I'm not going to mess with simplifying that anymore. I need a prime factor tree to reduce 18. 18 is 2 times 9, which is 3 times 3. My calculator is in complex mode right now, and it doesn't do factor trees in complex mode, and I knew I could do this quickly rather than getting it out of complex mode. So the 18 is going to reduce. It already has a 2 outside the radical. It's going to pick up a 3 outside the radical from the pair of 3s. It's going to have a 2 under the radical and still the I after the radical. So the 18 piece is going to come out to be 6 times the square root of 2 times I minus 5 times the square root of 2 times I. Now I'm just going to minus the 6 minus 5 and get 1, which you won't have to write. My calculator won't write it. But the answer is going to have a square root of 2 and I, and then you really don't need to have the 1 to the left of it, but you can. Again, I can do this all on my calculator as well. So 2 square root of negative 18 minus square root of negative 50, and I get square root of 2 times I without the 1. I knew my calculator wouldn't write the 1. To do 12 by hand, the square root of negative 9 is 3i. The square root of negative 4 is 2i. 3i times 2i is 6i squared. I squared is negative 1, so 6i squared is the same as 6 times negative 1. My answer to number 12 is going to be negative 6. If I want to check this, I just go square root of negative 9, get out of the square root, times sign square root of negative 4. Should tell me that this is negative 6, and it does. I'm solving a problem with a square root, so I need to get rid of the square root. I get rid of square roots by squaring both sides. So in problem 13 that says the square root of 2 minus 5x equals 8, I square and square. Squaring cancels out a square root sign, and it leaves me with 2 minus 5x. 8 squared is 8 times 8, which is 64. Now I'm going to minus 2 from both sides and get minus 5x equals to 62. And then I'm going to divide both sides by negative 5. The fraction doesn't reduce, but it looks bad having the negative in the denominator. My calculator won't put it in the numerator. My calculator will write it to the left of the fraction. But I like it in the numerator best. So my answer should be checked, but it's negative 62 over 5. I'm going to check it by going to the original problem, going, is the square root of 2 minus 5 times negative 62 over 5, does that equal to 8? So check, square root of 2 minus 5 times fraction negative 62 over 5, close my parentheses. If my answer is right, when I hit equals, it's going to say 8. If my answer is wrong, it won't say 8. And it says 8, so I know I haven't made a mistake. To do 14, I'm going to write this in radical form. 1/2 power can be written as the second root of the quantity to the first power. So writing something with a fraction exponent in radical form, you get the index becomes the denominator of the fraction exponent. Everything else goes under the radical. The 2, if I don't write a 2, there's an assumed 2. And similarly, if I don't have an exponent, it's assumed 1. So 1/2 power can be transformed to square root. And now I'm going to square both sides. On the left side, squaring cancels out the square root, leaves me the stuff under the square root. On the right side, 2 squared is 4. I'm going to add 3 to both sides and get an answer of x equal to 7, which I should check, and I should check it into the original problem. The original problem had a fraction exponent, and that's not hard for me to enter on my calculator. So I should make sure that 7 minus 3 to the 1/2 power equals to 2. So I'll do that quickly. Parentheses, 7 minus 3, parentheses, exponent, fraction, 1/2 power, and I get a true checking. Because when I plug 7 in for x into the problem before I tweaked it, I get a true statement. My answer is correct. (15) wants me to find the domain in the range of a few different graphs. The first graph has a period on the left edge, so the left edge doesn't need to be extended, but the right edge doesn't have a period, so it gets extended. It gets extended to the far right edge of the x-axis, which is the positive x direction, and the bottom of the y-axis, which is the negative y direction. To do the domain, you need to find the x-coordinate of the most left point The most left point is the point -1, 0. When I write the domain of this problem, I'm going to have -1 written first, and then I need to find the x coordinate of the point that's furthest right. The point that's furthest right is the extended point, positive infinity, negative infinity. Its x coordinate is infinity. Infinities generally get round brackets. Points that are on the graph get square brackets. So domain from a graph that has points connected, you do x coordinate of the far left point, then x coordinate of the far right point. The range of a graph that's points are connected, you need to find the y coordinate of the bottom point and the y coordinate of the top point. The bottom point is this extended point. Its y coordinate is negative infinity. The point 1, 4 is the top point. Its y coordinate is 4. And I did appropriate with the rounding square parentheses. I won't take points off if you have a square bracket when you need a round bracket. But in Math 151, your teacher might. The second part of number 15, because the points aren't connected, when you do the domain and the range, you just pick off the x and the y coordinates. So for the domain, I'm going to say it's -3, 1, 4, and 7. When the points on the graph aren't connected, you write the domain and the range using the set braces. The domain's the x coordinate of each of the points. The range would be the y coordinates, 4, 0, 0, and 2. It probably would be better, this is correct, but probably be better to write the range without writing the 0 twice. And it's probably nice to write it in ascending order, but I would give you credit if you had what I have written in black or that. The domain just kind of came out nicely. There was no points that had duplicate x's. I wrote them in ascending order. That's the best I could do. The range, when I started reading my points off, the numbers weren't in ascending order, and I had double 0 that I didn't need to write. 16 wants me to do some work with some functions. First one wants me to find f of 5. I find f of 5 by going to the f function and changing the x to 5. So I'm going to go 5 minus 3 times 5. It's just the orders of operations now. This is going to be 5 minus 15. So when I write my answer, I can write f of 5 equals -10. Or I can say y equal to -10, but I can't say x equal to -10 because x is 5. If I wanted to do this on my calculator, I'd just go 5 minus 3 times 5 and get that -10. h of -4, I'm going to change inside the absolute value 3 minus -4. Because I had a double negative, I made that double negative in a parentheses. And then h of -4 is going to be the absolute value. The double negative goes positive. So I get h of -4 equals the absolute value of 7. And the absolute value of any number, single number, is that number made positive. If the number is negative, I make the number positive and drop the absolute value signs. If the number is positive, I just drop the absolute value signs. So my answer to part B is going to be h of -4 equals to 7, or again, y equal to 7, x is -4, so it would be wrong to say x equal to 7. On the next page, C calls out g of 7, so I need the g function, and the g function is g of x equals x squared. To find g of 7, I just have to do 7 squared. I could do it with or without a parentheses. 7 squared I don't need my calculator for. That's 7 times 7, which is 49. So for my answer, I could write g of 7 equals to 49, or I can write y equal to 49. Both would be okay for an answer. In fact, if you just wrote the number 49, I'd be content with that. 17 wants me to reduce something that's harder to reduce. And if I want to do a factor tree for the 24 to reduce it, I need to get into a different mode. I'm in complex mode. It won't do factor tree, so I hit mode and 1 for computations. Now I'll do a prime factor tree for 24. 24 equals shift quotes. 24 equals to 2 times 2 times 2 times 3. I'll need that in a second. So to reduce this problem, I'm going to work with the 24 I'm going to work with the x to the 5th, and I'm going to work with the y to the 7th. This is a cubed root problem. It's the cubed root of 24 x to the 5th, y to the 7th. So every time I have 3 of a kind, I get 1 outside. So for the number 24, I'm going to have a 2 in front of the radical, and a single 3 is going to go under the radical. For the x to the 5th, I have 3 x's, so I get 1 x outside the radical, 2 x's under the radical, which I'd probably multiply back together and make an x squared. For the y to the 7th, I get 2 y's outside the radical. I'll write that as a y to the 2nd power, and a single y under the radical. So this is the best I can do for an answer, and this one isn't as checkable as I'd want it to be. So this is 2xy squared times the cube root of 3x squared y. I suppose I could make up numbers for x and y and put them into the original problem in my answer. Let me do that. Let me just go, let x equal to 2, y equal to 3. In the original problem, I could do the cube root of 24 times 2 to the 5th times 3 to the 7th. So shift cube root of 24 times 2 to the 5th times 3 to the 7th. And my calculator gives me 118.869. If I go to my answer and go 2 times 2 times 3 squared times the cube root of 3 times 2 squared times 3, changing the x to 2 and the y to 3, so I'd go 2 times 2 times 3 squared times the cube root of 3 times 2 squared times 3, and I get that same lovely 118.869. So I could check that just like I checked problems in Chapter 2, the Chapter 2 kind of problems. When you don't have equal signs and you have x's and y's in your answer and your original problem, you could just make up numbers for x and y, plug them into the original problem for the letters, plug them into the answers for the letters, and your reduction has to match. '18 wants me to do a nice friendly problem. It's a friendly problem because 64 is a perfect cube, so I can just do this on my calculator cleaner. So to do the cube root of negative 64, that's asking me what number times itself 3 times is negative 64, and that's negative 4. So in my answer, I'm going to have the number negative 4, and then anytime we have a letter, if its exponent is divisible by the index, the quickest way to reduce the letter to get it outside the radical is to do that division. So for this problem, if I divide the exponent on the x by 3, I'm going to get x to the 4th, and if I divide the exponent on the z by 3, I'll get z to the 5th. I claim this is the answer, which means I should be able to do the same thing. Plug in 2 for x, 3 for z. So for my checking, I'm going to let x equal to 2, z equal to 3, and see if the cube root of negative 64 times 2 to the 12th times 3 to the 15th, that might be too much for my calculator to handle, because 3 to the 15th is a pretty big number. See if that equals negative 4 times 2 to the 4th times 3 to the 5th. I'm worried about this a little bit, but I'll try it anyway. So for this version, plugging it into my answer, the cube root of negative 64 times 2 to the 12th times 3 to the 15th equals, oh my gosh, negative 15, negative 15552. For my answer, I'm going to go negative 4 times 2 to the 4th times 3 to the 5th, and I get that same negative 15552. So I feel good about my answer because taking random numbers, plugging it in for the variables in the original problem, and my answer, because they match up, I almost have to be right. 19a is not even something I probably need to check. When you're subtracting, If you have the same square root and the same letters, you just subtract the numbers. So for this problem, I just have to subtract the 4 minus 9, and I'll get negative 5. And the letter part doesn't change. So I'm going to get negative 5x, and the square root part doesn't change. If I wanted to, I could check. Let me just check by putting x equal to 2. I'll put x equal to 2 and go 4 times 2 square root of 3 minus 9 times 2 square root of 3. And then in my answer, I'm going to go minus 5 times 2 square root of 3. In my answer, I get minus 10 square root of 3. I'll do this on my calculator here. So 4 times 2 square root of 3 minus 9 times 2 square root of 3. And my calculator tells me that's minus 10 square root of 3. Which is exactly what I got when I changed my x and my answer to 2, because these things match. I know my answer is correct. B I could do on my calculator, but I'll do it by hand. I'll do a prime factor tree for 50 to reduce it. 50 equals shift prime factor. 50 equals 2 times 5 times 5. So for the 50, I'm going to get a 5 outside the radical and a 2 under the radical. So this 2 square root of 50 plus 5 square root of 2 problem can be changed. The 50 has a 2 in front of the radical. I'm going to bring a 5 in front of the radical and a 2 under. So I'm going to make this 10 square root of 2. And the 5 square root of 2 is not reducible because the 2 is a prime number. It doesn't have any pairs. Now I'm just going to add the 10 and the 5. And I'll get 15 square root of 2 for my answer. I can enter this problem like this on my calculator to check. So checking 2 square root of 50 plus 5 square root of 2. And I get 15 square root of 2, so I know my answer is correct. That's my favorite kind of checking, when my calculator does the problem. And in my calculator, we'll do part A as well. Part A, to do it by hand, I'm multiplying 2 square roots. I get another square root. I multiply the 2 and the 10 and get a 20. I do a prime factor tree for 20. 20 is 2 times 2 times 5. So when I reduce the square root of 20, I'm going to get a 2 outside my radical and a 5 under my radical. Easy to check on my calculator. Square root of 2, square root of 10 next to each other means times, and you get this 2 square root of 5. B is a foiling problem. Firsts are 3 times 3, which are 9. Outers are 3 times minus square root of x, which is minus 3 square root of x. Inners are positive square root of x times positive 3. That's positive 3 square root of x. Last, positive square root of x times negative square root of x. That's negative square root of x squared. Outers and the inners cancel. I get 9 minus, and for the square root of x squared, because x squared is just a couple of x's, I get an x outside the radical and nothing under the radical. So this would just be 9 minus x. And again, I can check by plugging 2 into my original problem in my answer. So if I wanted to check, I like x equal to 2 if it's not a domain error. So I'm going to go 3 plus the square root of 2 times 3 minus the square root of 2. And in my answer, I'm going to go 9 minus 2. In my answer, when I plug 2 in for x, I get 7. Hopefully this comes out to 7 as well. So I'm going to go parentheses 3 plus square root of 2 times 3 minus square root of 2, and I get 7 as well. So I've checked the best I can. So when your problems don't have equal signs and they have x's in the problem, the best you can do for checking is to make up a number, plug it into the letter in the original problem and in your answer, and if you get that beautiful matchup, then you're okay. 21 wants me to solve using square roots. And to solve using square roots, the problem has to have the square term isolated. So I'm going to minus 40 from both sides. On the left side, when I minus 40, I'm going to be left with that x minus 3 squared. On the right side, 56 minus 40 is 16. To solve by square roots, I go square root plus or minus square root. On the left side, square rooting cancels out the square, leaves me with x minus 3. On the right side, the square root of 16 is 4. I add 3 to both sides and get x equals 3 plus or minus 4. I make up the two problems implied. X equals 3 plus 4. X equals 3 minus 4. 3 plus 4 is 7. 3 minus 4 is negative 1. I think I get two answers, x equal to 7 and negative 1. I should check both. First one I'm going to check is 7. Going to the original problem, I'll go 7 minus 3 squared plus 40. That should be 56 if that's a true statement. So checking, I go 7 minus 3 quantity squared plus 40. Because that equals 56, 7 is an answer. Now I'm going to check negative 1. I'm going to go negative 1 minus 3 squared plus 40, and hopefully that also equals 56. So negative 1 minus 3 squared plus 40, and I get 56 equals 56 again. So I've checked, and I know my answers are right. 22 wants me to pull out the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac over 2a. I don't like the a being negative, but I can deal with it. My a is going to be negative 3. My b is going to be 4. My c is going to be negative 1. I'm going to go x equals to negative for the b, and then the 4 from the b, and then plus or minus the square root of 4 squared minus 4 times a, which is negative 3, times c, which is negative 1, over 2 times negative 3. Doing these on my calculator, I'll do the plus first, the minus second. So on my calculator, the best I can, fraction negative 4 plus square root 4 squared minus 4 times negative 3 times negative 1 over 2 times negative 3. And I get a lovely 1/3. And then I'm going to back up, hit my left arrow until I can get to that plus sign there and change it to a minus. So left, left, left. Eventually I'll get up to that plus sign. I'm going to delete it, change the plus sign to a minus, hit equals, and I get 1. I'm going to check both of these answers because they're checkable. Don't have a lot of room to check, but I'll squeeze it in here. I'll do it right up here. So for checking the 1/3, I need to go, is negative 3 times 1/3 squared plus 4 times 1/3 minus 1, does that equal to 0? So first check, negative 3 parentheses fraction 1/3 parentheses squared plus 4 parentheses fraction 1/3 parentheses minus 1. Best to get a 0 when I do that, and I do, so I got 0 equal to 0, so I know that I haven't messed up there. And then for the next one, I'll go negative 3 times 1 squared, that's checking the 1, plus 4 times 1 minus 1, and see if that equals to 0. Much easier to do. So negative 3 times 1 squared plus 4 times 1 minus 1, and I get 0. So I checked both of them, so I'm confident in my answers. Again, notice anytime a problem has an equal sign and I get answers x equal to some number, y equal to some number, I'm going to check. (23) wants me to do the u method, so I'm going to let u equal to x minus 3, and I'm going to write this as u squared plus 3u plus 2 equals to 0. I'm going to factor that. That factors into u plus 2 times u plus 1 equal to 0. I go u plus 2 equal to 0, u plus 1 equal to 0. I minus 2 from both sides and get u equal to minus 2. I minus 1 from both sides and get u equal to minus 1. Then I set the x minus 3, which is u equal to negative 2, and the x minus 3, which is u equal to negative 1. I plus 3 and plus 3 and get x equal to positive 1. I plus 3 and plus 3 and get x equal to positive 2. So my answer should be x equals to 1 and 2. And again, I'm going to check. I have some room right here to check the x equal to 1. I'll go is 1 minus 3 squared plus 3 times 1 minus 3 plus 2. Does that equal to 0? So easy enough to do that. So parentheses 1 minus 3 squared plus 3 times parentheses 1 minus 3 plus 2. That equals to 0. So I know that's fine. And now I'm going to change and go, I'm going to change the 1's to 2. So I'm going to go 2 minus 3 squared plus 3 times 2 minus 3 minus 2 equal to 0. So it's real easy for me to check the 2 now. I just use my back arrow, delete the 1, change it to a 2 in the second parentheses, go to the first parentheses, delete the 1, change it to a 2. When I hit equals, I'll get 0 equal to 0 again. So I've checked both of these by taking the numbers for x, separately plugging them into the original problem for both of the x's, and simplifying. I'm left with a true statement. Ugh. I'm going to change 25 here real quickly. I don't like that problem. I don't want to graph with ugly fractions, so you won't see that. So 24 wants me to sketch a graph, find the axis of symmetry. It's a parabola. When I have a parabola with the parentheses, I change the sign of the number in the parentheses. So the parentheses had a negative 2 in front of it. I change that negative 2 to a positive 2. And the table I'm going to use here is 0, 1, 2, 3, 4. And I'm going to get my y's by going mode 7. And then I go alpha x, whoops, I forgot my parentheses, alpha x minus 2 squared plus 1. Table start 0, table end 4, step 1. So my first point is going to be the point 0, 5, then 1, 2, then 2, 1, then 3, 2, and then 4, 5. So I'm going to plot the points now. So the first point is the point 0, 5. It's right on the y-axis. And then the point 1, 2, the point 2, 1, the point 3, 2, the point 4, 5. Graph should point that parabola out to you. Well, and your graph should actually go through the points, more or less. This is the vertex. I always make it so my table has the vertex in the center. So I want to say what the vertex is. The vertex is the point 2, 1. The axis of symmetry is always x equal the x coordinate of the vertex, so the axis of symmetry is x equal to 2. When you print out this, you won't see that horrible fraction for problem 25. You'll see this for your problem 25. Another one where I'm supposed to sketch a graph, a little bit harder because of the plus sign. My table's going to have a bunch of negative signs in it. So I'm going to change the sign of the number inside the parentheses, and I'm going to use for my table -7, -6, -5, -4, -3. I found -5 on the x-axis. I stepped over 2 to the left, and I did 5 consecutive points. Now I'm going to get my y's by doing a table. So mode 7 for table, f of x is -2 times alpha x plus 5 squared minus 4, start at -7, end at -3, step 1. So I get -12, -6, -4, -6, -12. I'm only going to plot these points, and if that's enough, it's not the optimal, but I don't feel like incrementing all the way down to -12. On the final exam, you'll be given a grid that looks like this, so it'll be easy to plot. And I'll make the points fit on your grid or coordinate system. So I'm only going to plot 3 points. So -6, -6, -5, -4, -4, -6, and the best I can kind of draw a U through them. So that's not a stellar graph, but it's good enough. That's the vertex. So I'm going to identify the vertex. The vertex is the point -5, -4. Because the vertex is at the top of the parabola, the vertex is a maximum point. If the vertex was at the bottom, it would be a minimum point. But this vertex is a maximum point. And the y-coordinate of the vertex is going to be the maximum y value. And that's everything that I need to do for problem 25. 26 only asks me to find the vertex. So I can just do that, or I can sketch a graph if I feel the need. I'm trying to make your life a little bit easier, but I'm going to go ahead and pretend that I didn't know how to do the vertex without doing a whole graph. Because there are 2 x's, to get my table started, I have to use the -b/2a formula. The a in this problem is the number in front of the x squared, which is -3. The b is the number in front of the x, which is 6. So for my table, I'm going to go -6 over 2 times -3, which is going to be -6 over -6, which is 1. Put 1 in the middle of my x column. The table I'm going to use is -1, 0, 1, 2, 3 to get my points. So mode table -3 alpha x squared plus 6 alpha x minus 1. Start at -1, stop at 3, step 1. I get the point -1, -10, 0, -1, 1, 2, 2, -1, 3, -10. So let me plot. I'm only going to plot 3 points again because I don't feel like going all the way to -10. So 0, -1's about there. 1, 2 is about here. 2, -1's about there. So the graph looks something like this. And the only thing the problem wants is me to say the vertex. So I really don't need the graph because it doesn't ask for a graph. It asks me to find the vertex. I did overkill because I graphed, but I got the answer anyways. So when you have a quadratic, or something with a square, and there's 2 x's, to get your table started, you had to use the formula. The last 2 problems that had the parentheses, I was just able to change the sign of the number in the parentheses, and that helped me get my starting table. But when there's 2 x's, the numbers in the problem aren't likely going to point you to the table exactly until you use the formula. Ugh. 27 wants me to add these 2 functions. When I'm adding functions, I don't need parentheses. So I write the right side of the f function, which is 2x, then the right side of the k function, which is x squared. That is an answer, but it definitely can be written better. I can write it with the x squared first. And I can certainly factor. Generally, you factor when you can. So the best answer to problem 27 is f plus k of x equals x times x plus 2. For 28, to find h plus k of 8. First I'll find h plus k of x. That will be the right side of the h function first, then a plus sign, and then the right side of the k function. I don't need to simplify that, but I do need to change the x to an 8. And this is going to be the square root of 8 plus 1 plus 8 squared. Might as well just do that on my calculator. So mode 1, square root of 8 plus 1 plus, I'm under the square root still, plus 8 squared, and I get 67. By hand, I'd go h plus k of 8 equals the square root of 9 plus 64, and h plus k of 8 equals to 3 plus 64. For my answer, I can say h plus k of 8 equals 67, or I can say y equal to 67. I can't say x equal to 67. X is actually 8. Oh, 29 wants me to compose f composed with k, so I need to know what f and k are. F of x is 2x. K of x is x squared. To do f composed with k, we replace the x in the f function with the k function, and you need parentheses. So I'm going to replace the f in the x in the f function with the x with the k function. Replace the x in the f function with the k function. And so f composed with k of x is just going to be 2 times x squared. Actually, I don't really need the parentheses here. If I write that without the parentheses, it still means 2 times x squared. So this is one of the rare times I was able to do composition without parentheses. For 30, I need to know the g function. The g function is 2 over x plus 4. I need to know the h function, which is the square root of x plus 1. First, I need to find g composed with h of x. To do that, I write the g function without the x. I replace the x with the h function. So g composed with h, I replace the x in the g function with the h function. That's just what I did. Now I want to change the number, the x to 8, because the problem asks me to change the x to 8. So I'm going to get 2 over the square root of 8 plus 1 plus 4. Might as well do it on my calculator. This is another time those parentheses aren't really necessary. The square root works as a parentheses just fine. So fraction 2 over the square root of 8 plus 1 plus 4, and I get 2/7 for an answer. Without my calculator, this would have been the square root of 9, which is 3. The denominator would have been 3 plus 4 to give me that 7. The numerator is already 2. (31) wants me to write with a logarithm. So I'm going to write the word log. The 2 that's the base is going to remain the base, and I'm going to switch the -3 and the 1/8. So I'm going to write the log. The 2 will be the base, and I'll switch the -3 and the +1/8. So write the word log. The 2 stays low. I switch the 1/8 and the -3, and I'm done. 32, write without a log. It might not be readable. It's a log base 4 of 64 equals to 3. To do that, you scratch out the log. Just the opposite. I'm going to leave the 4 low, and I'm going to switch the 64 and the 3. When I do that, I get 4 cubed equals 64. Still got a ways to go, huh? This goes all the way up to, oh, those are just some answers there. Goes all the way up to 39. So a little, not so much. We're getting closer to the end here. 33, to expand, you write one log for each letter. So I need to have a log base 5 for an x, a log base 5 for a y, and a log base 5 for a z. Any letter that started in the denominator, its logarithm needs to have a minus in front of it. So the only logarithm that needs a minus in front of it is the z log. Any other log, the only signs I'm putting in are minuses or plus, so they have to have plus signs. And that's the best we could do for 33. That's expanding. 34 wants me to go backwards and make 3 logs into 1. I start off 34 by making the 2 in front of the y logarithm an exponent on the y. Now I'm ready to make the 3 logs into 1. Because there isn't a minus, I don't need a fraction. I just need to multiply each of the letters. And I could put them in a parentheses. It'd probably look better if I did that. But a lot of times I don't. So there was no need when I make a single log out of 3 logs to have a fraction because there wasn't a minus. If any of the logarithms had a minus in front of it, that letter would have been buried in the denominator of a fraction. I'm going to do 35 and 36 both with logarithms, even though I don't have to. So I'm going to write the word log. I'm going to switch the x plus 1 and the 8. So I get the log base 2 of x plus, log base 2 of 8 equals x plus 1. I'm going to solve for x. I get minus 1 plus the log base 2 of 8 equals to x. And then I'll break out my calculator. So minus 1 plus the log base 2 of 8 equals to x. So 2 equals to x. I can check that. For checking, I'm going to go to this x and see if 2 to the 2 plus 1 equals to 8. So 2 to the 2 plus 1, and it does equal to 8. I'm going to do 36 the same way. I'm going to round to 2 decimal places. I don't see an instructions on rounding, but 2 is fine. So I'm going to write the word log. The 3 started low. It's going to stay low. I'm going to switch the x and the 15. So this problem, if you can't read it, says 3 to the x equals 15. You should have it printed out maybe in front of you. So this will give me the log base 3 of 15 equals to x. I'm going to do a 2 decimal accuracy. So log base 3 of 15. And I get 2.46 is approximately x for my answer, and I'm going to check. For checking, I'm going to see if 3 to the 2.46 power is about 15. It's not going to be very good. Let me carry more decimals. I'll do 3 to the 4.6497 power. I'll carry 5 decimals in my checking because it'll work better. So even though my answer only has 2 decimals, I'm checking with 0.46497 because it'll check better. So I go 3 up arrow 2.46497, and that's 14.9999 is approximately 15. So I'm pretty good, feeling good about that answer. 37 and 38, I both just scratch out the logarithms. So 37, the log base 2 of x equal to 3. I scratch out the log. The 2 stays low. I switch the 3 and the x. I get 2 cubed equals to x. 2 cubed is 8. So I get that for my answer. I should check. To check, I want to know if the log base 2 of 8 equals to 3. So real quickly, the log base 2 of 8. And this gives me 3 equals to 3, so I feel good about that. 38, same thing. Cross out the log and switch. The original problem is the log base 3 of x minus 4 equals to 1. Cross out the log. I get 3 to the 1 equals x minus 4. 3 to the 1 is 3. So I get 3 equal to x minus 4. I add 4 to both sides. I get 7 equal to x for my answer. Now I check and see if the log base 3 of 7 minus 4 equals to 1. So real quickly, log base 3 of 7 minus 4. And because it equals 1, I know I have a good answer. Last problem. I'm going to solve it like I did the last two problems, but it's going to be a little bit messier. Ultimately, these are the kinds of problems that we solved with cross multiplying, so I'll write the problem bigger again. When you have two logarithms separated by a minus, and you're trying to solve for x, you usually use the minus to divide rule, and that's what I'm going to use in problem 39. I'm going to use the minus to divide rule to make it so I only have one logarithm. Now I'm going to scratch out the log, leave the 3 low, and switch the 1 with the x, the fraction. So I get 3 to the first equals x over x minus 6. 3 to the first is just 3, so I get 3 equals x over x minus 6. Now I'm going to write it as a fraction and cross multiply, so I get 3 over 1 equals x over x minus 6. I cross multiply down and up. When I cross multiply down, I get 3 times x minus 6. When I cross multiply up, I get 1 times x. So this gives me 3x minus 18 equals 1x. I'm going to minus 3x from both sides and get minus 18 equals to minus 2x. And then divide both sides by minus 2 and get an answer of x equal to 9. And now I'm going to check. I'll check it right up here. See if the log base 3 of 9 minus the log base 3 of 9 minus 6 equals to 1. So the final exam review it's really designed to be kind of just the beginnings of your studying for the final exam, because one of each style of problem, it just can't be enough unless you just remember the things perfectly. If you've forgotten some of the problems, you're going to need to dig back in the other sections to fix what you don't understand. So it works, I get 1 equal to 1, so I've checked it perfectly. So I'm done with the final exam review. It should feel a little intimidating because the final exam is an intimidating test. It's a little bit harder than a regular test because it's comprehensive. So if you're not feeling good about a specific kind of problem, I've got plenty of time to help at the end of the semester. So come visit me, send me an email, and I can try to help you the best I can. If you need more guidance on what to study, come visit me in my office, and I can pick some problems from each of the sections, maybe each of the reviews, chapter reviews, to help you get more to study. But if only one of each style of problem is enough for you, then you're good. But if there's styles of problems that you didn't know how to do until I did them, then you should look for more practice, because that one of each kind of problem isn't going to be sufficient practice for when you take the final exam. All right, well, come visit me if you're feeling a bit overwhelmed, and I can try to make it less overwhelming.